Hello, all of you. My name is Sagar. I am a second year PhD student in Institute of Biophotonics, and my PhD advisor is a Professor Surojit Chattopadhyay. So, in the today's talk, I'm going to talk about one of my published work, which is on bismuth telluride gold nanocomposite Schottky junctions with the peroxidase activity for the glucose sensing. So, this is the schematic representation of my work where I have synthesized bismuth telluride gold nanocomposites, and it can give the peroxidase activity and also can use for the glucose sensing. So, before going to my work, I would like to tell you about a brief history about my work so that you will understand that what are the work which I have done in my study. So, so the first thing which we need to understand is enzymatic activity. So what does it mean by the enzymatic activity? So enzymatic activity is nothing but the conversion of a substrate into the product by using enzyme, which is also known as a catalytic activity. But in the case of enzymatic activity, majorly people use natural enzymes. So let's understand that how the enzymatic activity works. So the first thing which happens in the enzymatic activity is enzyme and substrate will get reacted with each other to form enzyme substrate complex. So later it goes under the catalysis to form this enzyme product complex, and instantaneously it form product and the enzyme it gets separate. So such a reaction is known as enzymatic activity. So, apart from this enzymatic activity, researchers have more focus on the artificial enzymes, which is also known as the nanoenzymes, because nanoenzymes are made up of nanoparticles which can give the activity like natural enzymes. So, why do we need the artificial enzymes? So, the reason behind that is the disadvantages of the natural enzymes. So the first reason of disadvantage of this natural enzyme is it's getting denatured very easily. The second disadvantage is it is very costly and it is very difficult to prepare, and it is unstable at under the harsh reaction condition. So due to these drawbacks, researchers have tried to uh, synthesize a new kind of materials which is known as a nanoenzymes. And the advantage of nanoenzymes are they can be easily tune their catalytic activity by just changing the morphology, and activity can be tuned. So this kind of nanoenzymes are very easy to prepare, and they are highly stable against denaturation. And these kind of nanoenzymes are very cheap in the price as compared to natural enzymes. So due to this reason, nanoenzymes is used nowadays majority. So let's understand that how many kind of nanoenzyme activities can nanoenzyme shows. So there are many nanoenzyme enzymatic activity can nanoenzyme show, but here I'm going to focus on the four major enzymatic activity. First is a superoxide dismutase activity, which can convert the superoxide anion into the H2O2 in the presence of nanoenzyme. So second activity is called as oxidase activity, where oxygen in the presence of substrate will get converted into the water and or H2O2, which is known as the oxidase activity. So the third category is the peroxidase activity, where H2O2 gets converted into the water or oxygen and or hydroxy radical. So the last part of the nanoenzyme is the catalyst activity, where H2O2 will get converts into the oxygen. So in my study, I was more focused on this peroxidase activity, as this three kind of catalytic activity have no much application in the real environment. So this peroxidase activity have much applications such as biosensing, immunoassay, and it can also use for the cancer cell imaging. So I have listed some of the applications of the peroxidase nanoenzyme. So the first application of this peroxidase nanoenzymes is we can easily identify the biotoxin. We can easily identify the metal ions just by looking the color of the solution. And small molecules such as H2O2 or glucose can be easily detected. Pesticides, some drugs, and bacteria or the cancer cell can easily detect just by the color, just by change in the color. So these are the applications of the peroxidase activity. So so far, how many kinds of nanoenzymes has been synthesized? So basically, in a broader perspective, there are four categories. So first is the noble metal-based nanomaterial, which is gold nanoparticles or silver nanoparticles. Second is the metal oxides, which is also such as Fe2O3 or the manganese oxide. So the third is metal chalcogenide based nanoenzymes where molybdenum sulfide, tungsten sulfide, or Fe sulfide has been used. So most of the metal chalcogenides are the transition metal chalcogenides where various transition metal chalcogenides such as vanadium sulfide, iron sulfide, cobalt sulfide, nickel sulfide has been used for this peroxidase activity. However, non-transition chalcogenides such as bismuth sulfide, bismuth telluride, bismuth selenide has not been reported yet. So the another major category of the nanoenzymes with the peroxidase activity is nanocomposites. So basically in this category, the metal oxides or the metal chalcogenides can be used, can be coupled with the gold, platinum or the silver to get the nanocomposites. So examples are MOS2 gold nanocomposites or graphene oxide gold nanocomposites. So these nanocomposites shows a better activity than their individual counterparts such as MOS2 or gold alone. So therefore, researchers are more focused on making the nanocomposite, which can gives the better peroxidase activity and even gives the limit of detection in the nanoscale. So the goal of my study is to demonstrate that the non-transition metal chalcogenides can also be used for the peroxidase activity. So non-transition chalcogenides are majorly bismuth telluride, bismuth selenide, and the bismuth sulfide. And there are other non-transitional chalcogenides are also available. However, in my study, I use bismuth telluride to show that this non-transition chalcogenides can be used for the peroxidase activity. So the second goal of my study was to demonstrate that this enhancement of the peroxidase activity is due to the formation of the Schottky junctions on this bismuth telluride gold nanocomposite. And the third goal of my study was to show that this non-transition chalcogenides can also be effectively used as enzymatic biosensors to detect H2O2 or glucose. So coming to my work, I have synthesized the bismuth telluride first by solvothermal method and TM image of these hexagonal nanosheets of bismuth telluride is shown here. So later I confirmed their composition by using EDAX technique, which is bismuth telluride is equally distributed all over the nanoplate and no gold was observed in the bismuth telluride alone. So second, I use these nano sheets and I make it a gold nanocomposite by in situ deposition of the gold nanoparticles on the surface of the bismuth telluride. So we can clearly see in the TM image the nanoclusters are deposited on the surface and some holes are created. So this created holes is due to the Kirkendall effect where some of the tellurium get replaced by the uh, mm, gold atoms. So later we confirm the the atomic deposition of the bismuth, tellurium, and the gold in this nanocomposite, and it is shown that the bismuth, tellurium, and the gold is equally distributed, and the distribution of the gold is highly dispersed in all over the nanoplates, which indicates that the deposition of the gold is very uniform on the nanosheet. So after confirming this nanocomposite, let's understand that what is a peroxidase-like activity. So the peroxidase-like activity is nothing but the conversion of H2O2 into the water on oxygen, and it get convert the substrate into the oxidized substrate. So typically, people use the TMB as a substrate, which is known as a 3,3-5,5-tetramethyl benzidine, and it is having this UV absorbance around 285 nanometer. And when it gets reacted with the nanoenzyme and the H2O2, it forms the lambda max at 370 nanometer and the 652 nanometer, this which is known as oxidized TMB, and the color of this solution is blue in color. So this kind of color can be easily seen by our eyes. So later we evaluated the peroxidase activity of our bismuth telluride gold nanocomposites, and we compared the catalytic activity with the bismuth telluride and the gold alone. So in the first case, we use bismuth telluride where no change was observed. It means no peroxidase activity was observed for bismuth telluride. Secondly, we use gold nanoclusters where slight peroxidase activity was observed in the slight change in the color, which indicates that the intrinsic activity of the gold nanoclusters. So third, we use our bismuth telluride gold nanocomposites where the color of the solution is turned colorless to blue in the presence of H2O2 and TMB, which means that the peroxidase activity can be enhanced by this kind of nanocomposites. So now we understand that okay, the H2O2 can be detected from the peroxidase activity by this nanocomposite. So we further evaluate the glucose sensing by this bismuth telluride gold nanocomposites where we use glucose and the glucose oxidase. So basically, when glucose will react with the glucose oxidase, it forms the H2O2, and the same reaction is happened in the presence of TMB and the gold nanocomposites. And therefore, we can see here in the presence of TMB, bismuth red gold nanocomposites, and the H2O2 formed due to the reaction of glucose and GOS can give this blue color. So this formed blue color indicates that we can easily sense the different millimolar concentrations of the glucose. So later we wanted to know that why this activity is enhanced. So to understand this, we have done the XPS study to find out the Schottky junctions between the bismuth telluride and the gold nanocomposites. So in the first figure, we can see that the bismuth peak is slightly shifted towards the left and the higher side when we use low and high amount, which indicates that there is a formation of bismuth and gold in these nanocomposites. In the second figure, we can see that tellurium 3D 5 by 2 and tellurium 3D 3 by 2 peak of bismuth telluride. So when there is a no gold in the reaction, we can clearly see the oxidized peak of the bismuth telluride is predominantly shown at 577 and 587 electron volt. When we use low amount of gold and the high amount of gold, this oxidized peaks of the tellurium is really suppressed, and which indicates that the gold is taking the place of the tellurium on this base material red gold composites. So this change in the bismuth and the tellurium indicates that there is a formation of bismuth gold bonding and tellurium gold bonding in the bismuth red gold nanocomposites. So further, we confirm this formation of the uh, this bismuth gold nanocomposites, and the gold shows that the conformation of the bismuth gold nanocomposites in the low concentration and the high concentration. So later, in order to know the mechanism of the our enhanced peroxidase activity from the bismuth gold nanocomposite, this is the schematic representation which I have shown before, and this is the actual reason why we have observed the enhanced peroxidase activity. So let's understand when there is a weak peroxidase activity, the gold has their intrinsic nature of activity. So that's why it gives the peroxidase activity. Whereas no POD was observed for the bismuth, right? So one thing we need to understand here is the work function for the gold is 5.31, and work function for the basic telluride is 5.3 electron volt. It means that when we get copper gold with the bismuth telluride, there is a higher possibility that electrons can easily pass from gold to the bismuth telluride at the interface. So this is what happened in our material gold nanocomposites, and we can see here the Schottky barrier, which has found in the gold and this material is only 0.14 electron volt. So this Schottky barrier is very small that electrons can easily pass through each other from gold to this material and can easily oxidize TMB into the oxidized TMB. So due to this reason, we observe that more number of electrons are available to get convert TMB into the oxidized TMB. So therefore, we observe the higher peroxidase activity. So the conclusion of our work is we have synthesized the Schottky barrier of this material gold nanocomposites, and it shows a 0.14 electron volt Schottky barrier. So second is this enhancement of the POD is observed in the bismuth telluride gold nanocomposite, which is much higher than the gold nanoclusters alone. So the third is we demonstrated that the peroxidase activity as well as glucose sensing can be done, and we also evaluated the limit of detection of the 0.38 millimolar. So the electron transport, the reason behind this peroxidase activity is the electron transport, which is responsible. Thank you.